Today I'm going to talk about Decibel, which is a system I worked on while I was at Coho Data, and this is joint work with Jake Wires and Andy Warfield. So to start off with, let me make this observation, that storage systems are a little like cheese. And by this, I mean that when you buy a storage service, whether this is a storage appliance from someone like EMC or NetApp, or whether this is hosted storage from AWS, Azure, or Google, it offers much richer functionality to the consumer than the underlying storage device that it's made of. In particular, typically storage services have offered things like data redundancy by transparently replicating the data for high availability. They've transparently aggregated devices to mask the seek latencies of spinning disks. And these are a global cluster-wide resource, so they're not tied to a single compute node in the system. And they're often decoupled from the underlying hardware, so the data can freely be migrated both by the consumer and the provider. It turns out that for all this functionality is not always wanted. And that's because there is a very real cost to providing it. And all these storage systems typically offer managed storage as an all-or-nothing proposition. So as a consumer, you end up either opting for it and then paying for a whole bunch of functionality that you don't necessarily want or need. A large number of recent data center applications have been written assuming unreliable storage. And these things handle fault tolerance and failure recovery by replicating data at the application layer, and they don't really benefit from having additional redundancy at the storage layer. I have 3 applications up over here. The paper talks about a few more of them. And if you read through the comments from different forums or deployment best practices, they really do recommend using direct local attached storage instead of managed storage. And the reason for this is the comments I've kind of highlighted. They talk about the latency cost of remote storage. They talk about the fact that you have performance unpredictability, and that it makes reasoning about performance a lot more complicated. So really, to summarize, it is that managed shared storage gives them lower throughput. It has higher latency overheads. And the fact that they're running on a shared device means that there's crosstalk and performance interference between different applications. Cloud providers recognize this, and today, this screenshot is from Google, but you can get this from any of the other major providers as well. You can opt for both managed and So you can opt for both managed and unmanaged storage from any of these providers. And there are a couple of things I would like to point out. Despite the fact that managed storage is replicated, it's actually cheaper than unmanaged storage. And this is largely because of the fact that local SSDs are tightly coupled to a single compute node and give providers much less opportunity to overcommit resources. And this results in resource wastage, which is passed on to consumers as cost. There's also a significant performance differential between these. You're talking about a 6 to 15x depending on the exact workload that you're running. So, as long as you're willing to pay the additional cost of local SSDs, you can just get these. And is this a solved problem? Well, it turns out that local SSDs are kind of inflexible to use. And this isn't really just an implementation issue, but a fundamental fact of them being tightly coupled to a single compute node. For instance, they don't always hold data. If you stop and restart your instance, they make migrations across nodes much harder. And this is not really what these fault-tolerant applications are looking for from their storage layer. So the question we asked ourselves was, is there some sort of useful intermediate point in between fully managed storage and local SSDs? Or put another way, is there something in between milk and cheese? Well, so to recap, managed storage provides applications with redundancy. It transparently aggregates devices. It's a cluster-wide global resource, and it's decoupled from the underlying hardware. Local storage has performance benefits, both in terms of throughput, latency, and isolation, but it comes with a tight host coupling and inflexibility. Now, for a large number of these applications, they would be willing to trade the durability and aggregation properties of storage for better performance, but would like to hold on to the flexibility and management benefits of managed storage. And to be clear, I'm not suggesting that this should replace fully managed storage, just as another point in the design space. In parallel with this application-facing need for different storage abstractions, data center providers are moving to disaggregated architectures. And this figure is from the Intel RackScale Architecture. And as you can see, it kind of divides clusters or racks into resource-centric modes. So you have entire regions which are storage areas and compute areas. And this essentially makes all local storage into a remoteness. But not all this remote storage needs all the properties of managed storage either. So Decibel is a storage service that gives remote clients local SSDs. And by this, I mean they're fast, they're isolated, they're low latency, but they run on a shared device. And they're a remote shared device. And all the storage is a subset of a single device. So they have the same failure properties as local SSDs. There are a number of challenges in providing this. Firstly, workloads tend to be dynamic, so we can't just statically partition the devices. Secondly, since they're running on a shared device, there needs to be some degree of virtualization and isolation. And all of this needs to happen at the line rate of devices, which is quite fast these days. To achieve this, Decibel is a two-part system. It introduces a virtualized storage abstraction, which I'm going to talk about first, and then there's a runtime, which schedules these abstractions onto the hardware to maintain the properties that we desire. So let me start off by talking about the abstraction. The storage abstraction in Decibel is kind of a hybrid abstraction. It's not a fully storage or a fully compute abstraction, but instead it's sort of a blend between the two. And by this, I mean that from the consumer perspective, this is a traditional storage, a network-attached block device. And it looks like a traditional storage volume. And this is why we call them Decibel volumes or DVOLs. From the runtime perspective, though, it's a resource container which needs to be isolated on top of a shared piece of hardware. And from that, it looks a lot more like a process or a virtual machine. Concretely, let me walk you through an example. I have, say, a Cassandra and a Kafka client which happen to be sharing a single device. And this exposes two virtual devices, one of which is hosting, the blue is the Cassandra storage, the orange is the Kafka storage. And this is fronted by a network service. And requests are routed to the front across the network boundary. This redirects them, demultiplexes to the appropriate, virtual device. And from the application perspective, this is what I mean. This is a traditional network-attached storage device, and it works over a TCP-based RPC library. Clients can link against, a client library that we have. From the runtime perspective, though, it needs to provide, virtual devices need to be isolated and need to preserve the performance of the underlying device. And because modern storage devices and NICs are extremely fast, virtualizing only the capacity is insufficient. We need to ensure that there are adequate CPU and NIC resources to make sure that requests can be served to clients in a timely manner. And so the abstraction that we really have is a vertical slice of the entire system, which is scheduled together: storage, memory, NIC, and the CPU. And this is the DVOL from the runtime perspective. The runtime then schedules these DVOLs down onto the underlying hardware. And so just to draw the analogy with the virtual machine, these DVOLs are full system resources with hardware-like interfaces, and they're isolated from one another but run on a fast shared piece of hardware. So what does the architecture of the runtime look like? Well, you've probably seen this figure before. This is the classical distributed systems in a box kind of architecture, which is Barrelfish, and then later on Arrakis and X. And each core in the system is treated as a completely independent entity. They're shared nothing entities. And we bypass the kernel completely and give them direct access to both the storage and the NIC using the Intel DPDK and SPDK. So each core has exclusive access to a single queue on each of these devices, and there's a tight queue-core-queue binding in user space. On top of these, since both of these are fairly low-level libraries, we have a user space TCP stack and a user space block IO layer. And on top of that, the Decibel logic sits and actually performs request processing. I'm going to blow that box out a little bit for the runtime. On each core, we have a single OS thread, and we cooperatively schedule all of this. Since both the DPDK and SPDK are poll mode drivers, we can precisely control how many cycles we are spending polling each of the devices, and the rest of the time we multiplex multiple devals onto the hardware. Now, each of the devals is tightly linked to a single core, but each core handles requests for multiple devals, so it's an n:1 multiplexing. Since each of the cores in the system is now a fully independent shared nothing entity, requests from clients need to be routed not just to the appropriate system in the network, but also to the appropriate core. And for this, we use flow director and hardware. This allows you to classify incoming packets on the basis of matching particular headers. So we have each core listening on a unique IP port combination. Now, one of the consequences of this decision is that devolves are bound both in terms of performance and in capacity to that of a single device and a single core in the system. In practice, in terms of the single core, we find that for today's hardware, we're able to saturate the device even using only a single core. In terms of the device limitation, this really does mimic what's available today with local SSDs. You're limited to both the capacity and performance of a single device. However, this binding between devolves and core is not a static property of the system. It's a dynamic one. And for this, we decouple placement from scheduling. Let me just tell you. For scheduling is a per core scheduler, and it focuses totally on making sure that all the devices are adequately being serviced and that the devolves are isolated from one another. Deciding where in the system a devolve is placed is a placement responsibility, and this is we use an external service called Mirador, which you can read about in the FAST paper. The reason we do this is that for a lot of workloads, devolves are created and then data is committed to them over time. So a priori knowing either the capacity or the performance requirements is hard. Instead, we just allow them to be placed anywhere and allow the controller to dynamically monitor for load or capacity imbalances and migrate these around to ensure that they have space to grow. So while both the DPDK and the SPDK give us this exclusive queue access, which allows these to function without locks, the underlying device is still a shared device, and we do need to handle some sort of allocation on that. Now, devolves want to be able to allocate storage at block granularity, but maintaining global state and updating it on block granularity causes a lot of contention. And for this reason, we borrow techniques from parallel memory allocators such as Hoard and tcmalloc, and we have per core caches. So storage is allocated to cores in 128 megabyte extents, from which the core can satisfy requests for any of the devolves that are scheduled on it. In terms of scheduling, we focus on, there's a two-part, we need to focus on holistically on making sure that we have efficiency and utilization across the entire system, as well as isolating devolves from one another. In terms of isolation, we focus on throughput isolation, and this is because the FTLs on these devices don't allow us to make hard guarantees in terms of latency. The paper has some more discussion about some recent emerging work on software FTLs and how these could be composed together. So for the isolation, this is just an experiment with 3 clients which are running with 3 devolves on a single core. And they're running against a single device with a 4K mix 7030 workload. One of them is, the top one is without any isolation, the left is throughput, and the right is latency. As you can see, one of these clients has a bit of a burst in the middle, while the other 2 remain static in terms of their workload. And without any isolation, the bursty client is able to go and interfere with the performance. It is able to take all the excess capacity on the device, but there is a corresponding drop in throughput and increase in latency for both the clients. For Decibel, we use deficit round-robin scheduling. And as you can see in the bottom, because it's a work-conserving scheduler, the excess capacity of the device is consumed by the bursty client, but both the throughput and the latency of the other clients are preserved. just want to point out that we're not particularly, committed. We use deficit round robin because it works quite well for us in practice. But devol's at a convenient hook point where you could put, there's been a rich body of work around other, storage isolation techniques, and we could implement these at that level. So the Decibel runtime, in addition to resource management and scheduling, also handles address virtualization, access control, and it uses some atomicity and data integrity on the devices. Those details are in the paper again. So how well do we perform? And for this, we try and answer two questions. First, what the performance of Decibel is against local storage devices, and secondly, what the single core performance is, because that's what the limiting factor for a single devol is. For our setup, we have a 1U server with 4 800 gig Intel P3700 cards and 2 40 gig NICs. And this, for a read-only workload, this is capable of 1.8 million IOPS, which is 60 Gbps. We test it using a 1U client, which also has 2 40 gig NICs. And the setup we use is that we have 2 clients per core, each of which has an independent devol on the server, and makes requests with a queue depth of 16. These are 4K random requests. So 2 clients per core, 2 devols per core on the server side. For the 70-30 mixed workload, you can see the performance numbers here. The blue line is the local device. The orange line is Decibel using a client which has been modified to use a DPDK network stack. And the green line is using the legacy network stack. The client in this case is a workload generator similar to FIO. And it's a little difficult to compare the latency because these hit saturation at different points, and the rest of the graph is just software queuing latency. So I've pulled these numbers out, but the DPDK client has about a 30 microsecond latency overhead, while the Linux client is about 70. For the all read workload, we kind of have a similar thing where we see about 20 microseconds overhead for the DPDK client and about 90 for the Linux client. Now, to test what a single devol can do, we take a core and a device and exclusively reserve it for one devol and test it with a single client at different queue depths. We test this with both the mixed 70-30 and the read-only workload. And we test it in 2 configurations, one with a queue depth of 1 to see what the minimum latency is, and one with at device saturation. We're able to saturate it in both cases with a queue depth of 64 in the mixed workload and with 96 in the read-only workload. And in all these cases, you can see there's about a 15 microsecond overhead for the remote case. So to summarize, today I've talked about Decibel, which is really trying to provide local storage or local SSDs as a kind of service where you preserve some of the properties of managed storage at the cost of reliability, but gain performance. And to achieve this, we encapsulate full system resources for a runtime and are able to achieve 20 to 30 microseconds overhead to local devices while preserving some isolation across clients. Thank you, and I'm happy to take questions.
Hi, nice work. I'm Wonso from NetApp. So you showed a latency graph, and then that's not average.
Sorry?
Did you?
Yes, these are average latencies.
Yeah. So did you happen to have the worst case latency values? Because you shared the one core with the multiple thread, and there's a round robin scheduling going on, and then somehow a usual latency maybe if the work that's scheduled to be later of the round robin queue, and then it's
So
more
the
latency,
worst
right?
case latencies tend to be more limited by the actual storage device. So at least for these devices, we see every now and again, these do hit millisecond and even full second latencies if you hit garbage collection loops and stuff like that. So it's more of a underlying storage device. And this is what I meant by there's been some work around compacting the FTL to get really reliable performance out of that. But without that, it's hard for us to really do much better because there's more variability from the device than our software stack on top of it.
Okay, so you didn't measure the worst case latency, basically. You don't have actually full distribution of latency, 90%.
I don't have those numbers, no.
If you don't have a question, let me ask one more. So these numbers based on NVMe cards, right? So
yes.
do you speculate that if there any faster device coming out, like an Intel Crosspoint, right?
Sorry?
Like the faster device like Intel Crosspoint, right?
Yes.
And then do you think that your system is work better than like the baseline?
What do you mean by base? So I have a graph against DRAM over here. And so, this is about it. So we can do about 23 microseconds, and this is, on this one we have much less variability because the underlying. So, and we can do pretty constantly at about 23 microseconds. Now this is DRAM, 3D Crosspoint is about 8x slower than this, but this is still slower than RDMA. But it's significantly faster than using, a legacy storage. So.
Okay, thank you.
All right, let's thank our speaker once again.